talk about sequences. And you've seen sequences before in other classes, but just to make sure that we're all on the same page, a sequence is a list of numbers written in a definite order. We could write it in a couple of different ways. We could write it with these lovely curly brackets around n over n plus 1. Or I could say a sub n is equal to n plus 1. Or I can actually write out all of this list. So this here I have figuring out what that first term is, that second term, third term, A1, A2, A3, and then up to a generic term. Sometimes you see it without the generic term, sometimes you see it with the generic term. So we can write them in any one of those orders, and we kind of think about it as a function where my domain is only the natural number. So we're talking about my inputs being 1, 2, 3, 4, 5, and my outputs being whatever comes out from my. So if I have the sequence a sub n is equal to n over 1 plus n squared, we're going to use n equals 1 as the first term, and I want the first 4 terms. So I would have 1 over 2, and then when I put 2 in, I'm going to get 2 over 1 plus 2 squared, so that's 2 over 5. And then when I put in 3, I'm going to get 3 over 3 squared is 9, plus 1 is 10. And last but not least, 4 over 17. Now, it's a lot easier to start from the explicit formula and give that list of numbers than it is to go from a list of numbers to the explicit formula. That can be a trickier problem. Now, we say a sequence converges to a limit, roll credits, as n goes to infinity if I am approaching a certain number. This can also be written as that notation, either one of those notations. So in this case, we're looking at the limit as n approaches infinity of n over 1 plus n squared. Okay, taking a look at that, we know that this is a situation where we are bottom heavy. We are growing faster on the bottom than we are on the top, and this limit is approaching 0. Okay, so we could, and again, I could follow all of my limits rules that we've seen before. So L'Hopital still applies. All of that built-in knowledge that we already have can come back and evaluate these limits. Then we want to know, does this one converge? And if so, to what value does it converge? So we're looking at the limit as n goes to infinity of ln of 1 plus 2 over 2. Okay, so right now I know if I plug in infinity, I'm getting infinity over infinity. And go ahead and try. Think about what you want to do based on the fact that I'm getting infinity over infinity, and go ahead and try that. Hopefully you took a moment to try that. So again, I have an infinity over infinity, and we're going to use L'Hopital's here, because L'Hopital's applies. So I'll get the limit as n goes to infinity of 1 over 1 plus 2e to the n times another 2e to the n, chain rule, over 2. Limit as n goes to infinity, 2n, another 2. Oops. Kind of like that. Now, what I would do is I would probably multiply top and bottom by 1 over e to the n. And what I'll have here is 2 over e to the n plus 2. And now the limit as n approaches infinity. Now, this piece is going to zero out, and I get 2. So this piece zeroes out, and that limit is approaching 2 over 2 times 2, which is 1/2. You could have also used L'Hopital's again if you didn't like this little multiplying by 1 over e to the x. Okay, so this is converging to 1/2. Oh, the squeeze theorem. Okay, so squeeze theorem is when, just like I did it with limits earlier, I can still use squeeze theorem on limits here. And we're doing the limit as n goes to infinity of cosine of n to the n over ln of n plus 1. What I want to do here is I want to think about what two sequences I'm going to squeeze this between. Since the largest that cosine can be is +1 and the smallest cosine can be is -1, I'm going to look at if one of my sequences was 1 over ln n plus 1 and the other is 1 over -1. Okay, and so that's because cosine of n to the n over ln of n plus 1 has to be between these. Again, the biggest it could be and the smallest. So since cosine of n to the n has to be stuck between -1 and 1, we know that this sequence has to be between those two. So what we'll do is we'll find the limit as n approaches infinity of 1 over ln n plus 1. Well, as n gets really big, I'm getting 1 over ln of something humongous, and ln of something humongous is still going to approach infinity, and that limit is going to approach 0. Now when I do it the other way, the limit as n approaches infinity of -1. Same kind of deal. As n goes to infinity, n plus 1 is going to head to infinity, and ln of n plus 1 will head to infinity, really slower than n plus 1, but still go there. And -1 over something humongous is going to approach 0. Since this limit is 0 and that limit is 0, the limit of that one in between has to also approach 0 by the squeeze theorem. Squeeze theorem is really helpful if you have something complicated that you're really not sure how to, but you can give it bounds on either side. Alright. So on this one, a lot of times, in general, a lot of times you can have sequences that alternate from positive to negative, positive, negative. And there's a couple of common ones that we can see that'll help create alternate sequences. You could have a -1 to the n, you could have a -1 to the n plus 1. Sometimes you also see a -1 to the n minus 1. And then the oddball is like cosine pi n. That will also alternate. So here we're going to write some explicit formulas. Okay? So I want to think about what must be happening. Now I notice that they have an alternator. So I'm going to start with a -1. Okay, and now I have to think about this is my A1 and my A2. I want my first term to be positive, so I need to, there's a key n plus 1. So this one's starting for a negative. Well, this one starts off positive. Same with the n minus 1 also. So I have an n plus 1 here, n minus 1 would also work. And then 1 over, but now I gotta think about this. This is a 1. So I want some sort of sequence of numbers where the first number is 1, second number is 2, next number is 6, and then the next one's 24. So something that goes 1, 2, 6, 24. You might recognize that. You might not. What I do notice, 1 times 1 is 1. 2 times 1 is 2. 6, that's 1 times 2 times 3. Oh, and 24 is 1 times 2 times 3 times 4. So really what we have there is an n factorial. Go ahead and try 4b as well. Okay. Now, all right, we want, hopefully you tried it. Did you pause the video so you could try it? Okay. Here we want it to start negative, so I'm going to start with a -1 to the n. Basically. And then 4, 6, 8. So that's a nice little 2n on the top. And on the bottom, I have 3, 5, 7, 9. So I can just do these are going up by 2 every single time. And we're going to say 2n plus 1. So there's one of those two. Again, it is harder to write these explicit formulas. You have to kind of look for patterns and things. So fill in a blank. A geometric sequence. Okay, so this is from when you did sequences and series, probably in pre-calculus. It's going to converge. Now, I'm not asking about the geometric series, but the sequence. Okay, so the list of numbers is going to converge when r is between greater than negative 1, greater than negative 1, and less than or equal to 1. Now, we wouldn't say the series would converge when r is 1, but the sequence does, because if r is 1, then my sequence is going to be a1, and then times 1, and then times 1, and then times 1. So the sequence is it's what we would call a constant sequence. So it is converging to a value because it's just whatever that starting term is. Okay. If my r is something like 1/2, then we're going to be approaching 0. A little bit of vocab here. Monotonic is something that's strictly increasing or strictly decreasing. Okay, we learned how to figure out if things were increasing or decreasing by taking their derivatives, and that's a really good tie-in to previously learned content. Bounded means that the function is bounded above and below, so I know that I'm always in the positives, or I know I don't exceed a certain number. Okay, so, and here's that same kind of information. We call it increasing if the next term is always bigger than the previous term. We call it decreasing if the next term is always smaller than the previous term. And so the same bounded above, bounded below. And every bounded monotonic sequence is convergent. So if I know that it's bounded and I know it's always either increasing or decreasing, then I must be approaching that bound. And that's lesson 12.1.